Welcome to a new Houdini course. We'll start by going over the Extract Transform node. This will allow us to replace the hammer in Craig's hand with any kind of geometry. Then we are going to simulate the flaming sphere itself by using volumes and particle advection. Using different SOP tools, we'll be able to refine the shape of our sphere. In the final lesson, I also go over how I set up this very simple comp in Nuke. The completed project files and assets will be available, just follow the link in the description. Hope you will enjoy, and let's get started. So let's see how this works, and I will go ahead and hide all of these render objects, and let's start fresh with a new geometry object, and let's rename this to FX Craig. Let's step inside and let's bring in our Craig test geometry. Let's go ahead and let's press S in our viewport, and I will go ahead and grab this hammer and I'll press delete so we can separate this from his body. So let's choose here delete non-selected, and we can work on this hammer for now. So to use the extract transform, we will need a reference geometry and a target geometry. It's important to note that both of these geometries must have the same topology. So what you can do, and this will work in 99% of cases, is just freeze the geometry that you have. So from this blast node, let's maybe go to the beginning of the timeline. I will drop down a time shift here. Let's Control Shift click this value here to remove the expression, and let's leave the frame as 1. So now our geometry is frozen. So this can become our reference geometry. I'll drop down a null and let's rename this to ref geo, and our target geo will be our regular geometry, so the one that has animation. So from this blast node, let's drop down a null and let's rename this to target geo. So the extract transform will work with both of these geometries, but since we might want to do some modifications here, this is actually packed geometry. So after this blast node, I can go ahead, I will drop down an unpack node and let's reconnect our nodes to this unpacked version, just so we are actually working with polygons and not with just one point. So again, our reference geometry will be this one frozen at the first frame, and our target geometry is going to be the animated version. So let's go ahead, drop an extract transform node and place the reference geometry in our first input and our target geometry in our second input. And the result of this node will be this point over here, and I will press D and let's just go ahead and make our points bigger. So let's go to points here and I will just increase the point size. Okay, so hopefully now we can see it. And this point is now storing all of the transform data. And in this case, if we look at the extraction method, we can see that it's extracting the translation and rotation. So if I scroll the timeline, we can see that this point starts to move, and essentially it's going to look at our reference geometry. So each frame, this will look at our reference geometry and our target geometry, and it's going to calculate for each frame the difference between the translation and the rotation of our moving geometry based on where our reference geometry is. So if I look at this point result now, we can see that it's roughly where our animated version is. So if we want to apply this transformation data back to our reference geometry, I can go ahead and let's grab this reference geometry and let's place this as our first input inside a copy to points, and let's use the target points to be our extract transform result here. So we are grabbing the static version of this hammer, and if I look at the result here for the copy to points, we are applying back our animation through this point over here from the extract transform node. Okay, so now we have our animation back, and we can see that this will match our initial Craig animation. So I can template this to make sure that this works, and we can see now that this perfectly matches the movement that we had originally. So now what we can do, for example, is we can alter our hammer geometry or create new geometry entirely and use our point data over here to make this geometry match our animation. So just as an example, from this reference geometry, I can go ahead and let's do a remesh on this, so we have more geometry. So over to the side I will place a remesh node, and it's important that you do this in a separate chain so that we don't change the topology of the reference geometry. So the topology of the reference geometry and the target geometry must be the same. So over here to the side, let's do this remesh and let's decrease the target size to maybe 0.03, so we have some resolution. Let's do a mountain SOP to add some noise, and this won't be a pretty result, but just to give you an idea of some of the stuff that you can do with this technique, let's go ahead and maybe drop down the element size a bit and adjust this slightly. And I'll also go ahead and turn on animation. So we have something like this, and if I plug this inside the copy to points, this will now follow our original animation. So we can also template our geometry, our crag animation, and let's press E here. Okay, so now our hammer has this noise applied to it, which follows the animation that we had. And the best thing about this is that this is very fast to compute, so we can see that I'm previewing this in real time. So maybe I can make this even more apparent. If I increase this amplitude for the noise, we end up with something like this. And to give you just one more example, if you were to have particles that run over this hammer and you want to stick those particles to the hammer, let's maybe go ahead and let's do from this reference geometry, we will drop this inside a popnet. And let's switch our display back to pixels. Let's step inside and let's just increase the count. So in the birth tab, let's maybe add another 0 here, and let's decrease their life to maybe a value of 2. And let's move them by using a pop wind, and I will increase the amplitude here to 1. And inside a geometry VOP, I will make these particles stick to our hammer geometry, so the first inputs. So inside this geometry VOP, I will go to inputs. Let's set the first input. Let's make this look at our first contact geometry, which is essentially ourselves. And let's go inside here, and we will just do a min pause from op input 1, and let's plug the P inside the position here. So this will just simply make our particles stick to this hammer geometry. So let's plug the result and let's play the animation. So this is what we end up with. Now there are better ways than this minimum position option here to make our particles stick to the geometry, but for the sake of speed, let's just use this version, and I'll go up and maybe adjust the swirl size for our pop wind, and let's take a look. Alright, so we can go up, and from here let's also color these particles based on their speed. So I will do another attribute VOP, and from the V I will generate a length, and let's also fit range this value, and we might as well do a ramp parameter, and let's leave this as color and plug this here, and let's promote the source max for our fit, and let's go up. Let's maybe choose a, let's do something like a blue, so something like this, and we can play around with the maximum value in source max. So if I look at the result, we end up with something like this, and I can just plug this inside our copy to points, and now this will follow our animation. Let's also template our crag geometry. So we end up with something like this. So the particles stick to the animation, and this is super fast, and I believe a really efficient way to make particles stick to objects. So these are just a couple of examples of how to use this. Now the cool part about this is we actually don't need this reference geometry to be exactly where the animation is, meaning that I can essentially place this reference geometry wherever I want in the scene, and this extract transform will give me the correct data. So I'll go ahead and let's remove these nodes, and for example what I can do is I will make some room, and from this time shift I will do a match size to bring this in the center of my scene, and I can also do a transform, and I can grab this geometry and I will just rotate this so it's sort of in a rest state. So it's aligned in all of the planes, and I can press spacebar and 3 and hop in some of these orthographic views, and I can press rotate, and I can try to match it so it's right in the center and aligned with all of our axes. So I can push this to the side, and let's also go to our other views, and I'm more or less just approximating where this geometry would be perfectly aligned in all of the axes. So let's try something like this. So something like this should be fine. And like I mentioned, we will still get the same result even if we move this reference geometry. So if I plug this back in our copy to points, we have the exact same result, and this will follow the animation perfectly. So we can check, and we can see that it does. And the power here is that if I go back to this reference geometry, we can have all of our effects right at the center of our scene, and we can also see that this is perfectly aligned vertically. And this is going to give us a huge speed boost, and it's going to be a lot more convenient to build our effects, because we don't really have to work with any weird angles and rotations. So if I were to disable these nodes, we don't have to build our effects in this position right here. So we can align everything nicely in the center of our world, and also perfectly vertically aligned. So also now if I were to replace this weapon with a sword or a bat, I will first add another transform node over here, and with my second transform node I will want to bring this up, this whole geometry up. So in the translate Y over here, so the middle value, I will just use my scroll wheel and I want to bring this up roughly to where we can imagine that Craig's hand is right in the center of our scene. So where he is holding the handle basically. Which means that if to the side I will do a tube, and let's template our reference geometry and look at our tube. Let's press enter and I will hold down shift and let's scale this in, and I will bring this up slightly and also bring the lower end up and try to match the size of this hammer, and maybe scale this in even more. I can replace now this hammer entirely with this tube geometry, and let's take a look. And up here let's actually duplicate this blast node, and I want to preview the result without the hammer. So let's press W on this to template the geometry, and let's look at our copy to points result, and here we have it. So this is what we have right now, and I can reverse the direction of this tube if I just do a transform here, and I just basically, if I just rotate this 180 degrees on the first axis, and let's go back. So now Craig is looking like he's holding a pipe and is about to lay down a beatdown on someone. Another thing that we can do is we can do another transform over here. So let's do a new transform and let's look at our hammer geometry, and we want to make this overall bigger. So let's increase the uniform scale. Let's try something like this, and let's go in one of the orthographic views, and we can see that we are working roughly from -1 here to 3, which gives us a size of 4 units. And the reason we are making this mesh bigger is because we also want our simulation to be roughly within these bounds. So usually when we're dealing with Pyro, you will get the best results if you work between 1 and 5 units for smaller scale effects at least. But if I were to disable this, we can see that we are only working with 1 unit basically, and this might be a little too small, so we will not get the best behavior for our Pyro. And also we would have to work with really small and sensitive values for the VDB resolutions, which we don't really want. So we just want to make everything larger, and the extract transform will take care of everything else. So we can simulate in this region here. Maybe I can just make this even bigger. Let's try a uniform scale of 4. So this might be a good size for our simulation. And in the extract transform over here, we also have to specify that we want the translation, rotation and uniform scale. So let's use this option instead. And now this will calculate the difference in size as well as the translation and rotation. And we can check that this works if I plug this reference geometry in our copy to points. We can see that when we copy this over, it's going to have the correct size. So this will match our animation. So let's go back. And now we can look at our tube and template the reference geometry. So press E on this. And we will also want to make our tube overall bigger. So let's press enter and let's bring this up and bring out the radius as well. So hold down shift and bring this out. So now we can use this as a reference for our simulation. And let's plug the result here into our copy to points and see how this will look. So this is currently the height. So this is currently what we have. Let's look through our camera. And for the flaming spear animation, we only want to simulate one side of it, and then we will just duplicate it and rotate it 180 degrees and slightly offset it to have the other side as well. So we are only going to focus on simulating one side. And probably this can still be a little bit taller. So let's go to this tube and I can increase the height. And we can also control with the center value here where we want this to start. So let's adjust the height and our center start. So this is going to be roughly the bounds of what I want the simulation to be. So while we work on the simulation, we will be able to reference the size of this tube to know exactly what result we're gonna get. So let's go ahead and we can grab this transform node and delete this, and also disconnect our tube, and I'll just leave this hanging here for now and we can start our simulation. So let's go ahead and also get rid of this copy to points, and in fact I will drop down a null from this extract transform and let's rename this to extracted point so we can refer to it later down the chain. And for our flaming spear effects, let's go ahead and start with a simple circle, And let's go ahead and template the tube and look at our circle so we know how wide the circle should be. And let's go ahead and set the orientation to ZX plane, and we will decrease the uniform scale to maybe a value of 0.3. And also let's just bring this up to the base of our tube where we want our simulation to start essentially. And I will adjust the uniform scale further to match our tube. So this should be fine, and I'll just increase the divisions here, so this will be a good base for our simulation. From here we can do a scatter. Let's turn off all of these options except the total count, and let's just have a few points, so maybe roughly 700 should be fine. And I want to source these points into a PubNet simulation, but first let's create a velocity vector for them. So let's do an attribute VOP, and let's rename this to set V. Let's jump inside, and for our velocity we will middle mouse click, and let's promote this to a constant. And for now let's just do a value of 0, 1 and 0, so this will essentially just point straight up. Let's go up, and it should be fine for now. So let's plug this inside a PubNet, and let's step inside. For our source, let's turn off the guide, and emission type should be all points. And for the birth, let's use a value of 1.5 and a life variance of 0.3. And let's see what this will give us. Alright, so that's pretty good. One thing that I want to do is let's randomize this velocity vector. So let's go up, and inside our attribute VOP, let's go inside here, and we want to generate a random value for all of our points. So from the ptnum, let's do a random, and let's multiply our vector with this random. And let's see what this will give us. Alright, so now we have more variation in the speed. Now the problem is that some of these points will now have a velocity that's really close to 0, essentially meaning that they hardly move. And I want any given point to have at least a velocity value of 0.1. So from this random, let's do a fit range. And let's set the destination minimum here to a value of 0.1. So now no particles can have a velocity value less than 0.1. Alright, and one other thing that we want to do is let's go up, and for this scatter, let's randomize the global seed for each frame. So inside the global seed value here, let's do $FF. So now every frame we will get a different set of points, and this will make our simulation more uniform. So let's go here, and this will be perfect. One other thing that we can do is we can introduce some more randomness. So before the set velocity attribute, let's go to our scatter, and let's add an attribute noise float, and we will set this to CD, and let's decrease the element size a bit. Let's try something like a value of 0.1, and we also want to enable remap ramp, and I will just bring this first handle in slightly to create some contrast. So we end up with something like this, and we want to turn on the animation as well. So let's check this, and let's see what we get. Probably we can reduce the element size even more, so let's try a value of 0.06. Alright, and let's decrease the contrast slightly, and now we have some color noise. And what we can do is we can get rid of the points that are completely black. So from here I will do a blast, and group type will be points. Let's delete non-selected, and for the group we will use expression at CD greater than 0. So now this will get rid of all of the completely black points. And this is more or less an optional step. I think we will have the same result in the end, but this is just something I usually like to do to optimize the simulations a little bit. But since we are not dealing with thousands of points, we would probably get the same result if we have this blast node or not. So let's go back to our PubNet and see our current result. And I think we can remove the display for the tube for now. And what we can do from here is I want to taper these points slightly towards the top, so we get more of the spear shape. So after we simulate for around a few seconds, let's go maybe at around frame 65, and we will do a taper. So let's drop down a linear taper, and if I press enter in the viewport, Houdini gives us a bunch of hotkeys to work with here. So first we will press N to fit our capture, and we can press B to cycle our capture to get the orientation that we want. And now I can grab this handle here, and I can just bring this in so we can achieve this tapered result. So now our simulation has sort of like this pointy shape to it, which will help with our movement down the line. So now these points can become a base for a Pyro simulation. Let's first create a density attribute. So drop down an attribute VOP from here. Let's rename this to set density. And we can base this density on our color, since we already have some variation in our color. So let's go inside here. Let's grab our CD. Let's do a vector to float. And I'll grab the first value here and do a bind export. And let's export this to attribute density. So now we can go up and let's drop this inside a volume rasterize attributes. The attribute here will be density. Let's do a voxel size of 0.05 for now, and later we will link this with our Pyro resolution. And for particle scale, I found that a value of 0.02 worked well in this case. So we end up with something like this. Don't worry, for now we will have to increase the resolution a bit. And let's also turn on velocity blur, and let's increase the shutter to 1. We will set the shutter offset to -1, and we will also increase the blur samples to maybe 10. So we also have a bit of smearing to our volume, and this will give us overall a smoother result. This should be fine, and now I can hold down Alt and duplicate this node, and here we can rasterize the velocity attribute, so the attribute will be V. And the reason we want to separate these two rasterized nodes is that I want to do some further modifications to our velocity attribute, and we want to have separate controls over this. So before our rasterized node, let's do a point velocity. And let's take a look here. Let's set this initialization value to keep incoming, because we already have the velocity. And we will go to the curl noise, and let's turn on this add curl noise option. And we can go ahead and preview our velocity in the viewport. So this is what we have currently, and I will reduce the scale to maybe 0.5. Let's also decrease this pulse duration to 0.7 and a swirl size of 0.3. Alright, and I also want to increase the grain here. Let's maybe do grain 0.65. So these are the values that I ended up with after doing some tests. Okay, so this is our new velocity, and now we can grab these rasterized nodes and we will hold down Alt to merge these. And we can plug the merged result inside a Pyro solver. So let's drop down a Pyro solver. And we can now go ahead and link the resolution of this solver. So let's right click, copy parameter, go to this volume rasterize, and let's paste relative references over here and do the same thing for our volume, for our velocity version. So let's right click here as well, and maybe we can rename this to rasterize density, and this can be rasterize V. And I will reduce the voxel size here. Let's maybe try a value of 0.05 while we do some experimentation. So let's take a look now and see what the defaults will give us. Alright, so this is the result, and we can see currently that it's a little bit too chaotic, and this is because if we go in our sourcing tab over here, let's get rid of the temperature and the burn as well. We only need to work with density and the velocity. So we can see here that the velocity is being sourced in as add. This means that each frame we add the velocity on top of itself, and it's making it accumulate. So we essentially gain way too much speed. And this can work great when we want to have explosions and more of a burst type effect. But in this case, what we want to do is let's use instead the pool version here. So this will be the more controlled way of sourcing. This essentially blends in the velocity in time and it doesn't accumulate. And we will have to leave this at vector, and we also need to turn on direction strength here. Let's leave this as 1, and we will just increase the acceleration here to 5. So let's look at our result now. So we can see now that this is a lot slower and more controlled, and this is what we are looking for. For the other options here, let's go to our fields and let's get rid of this flame field, and we will decrease the dissipation to 0.05, so this will make our smoke last a little bit longer. And in the shape tab, we want to turn on turbulence. Let's go ahead and let's map this to our density because we no longer have this temperature field. And for the values here, I found that a value of turbulence of 0.13 was okay, and swirl size, let's decrease this to 0.3, and let's also increase the roughness to maybe 0.6, and let's see what this will give us. Alright, so this starts off pretty alright, but after a while I think we're getting a little bit too chaotic, so we might want to decrease this turbulence. Let's maybe try a value of 0.06 and just increase the swirl size maybe as well. Let's do 0.6 and see what this will give us. Okay, so this is slightly better, but we can see that after a while even though we start off pretty alright, we end up with kind of a messy result. And in order to achieve more of a straight vertical shape, we can create an additional velocity field and source it in. So to the side here, let's drop down a box, which will essentially become the container of this velocity field, and I will template this geometry, press enter, and let's adjust the size so it roughly fits our currently simulation. So I will grab this handle here and let's bring this out roughly around the size of our simulation, and maybe I can grab also this corner here while holding down shift, and I will just scale this outwards a little bit as well. So let's do something like this. I believe this will be fine. Maybe we don't actually need this to be this thick, so I'll just scale this in slightly. Alright, I think this will be fine. So let's turn this box into a volume now and do a VDB from polygons. Let's set the voxel size, let's set it to 0.05. We don't actually have to link this with our solver resolution. We can just do a 0.05 value, and let's turn on fog VDB, and I will actually rename this from density. Let's do new vel with capital V, but you can basically give this any name. Now if we go to the information tab over here, we can see that this new vel field is a float field, so we need to turn this into a vector field. So let's do a convert VDB, and we will do convert to VDB. VDB class, let's leave this to no change, and VDB type will be vector float. So now if I go to the information, this becomes a vector field. So we will want to create a vector that points to the center of our scene. Let's do a volume VOP, and let's rename this to set V. Let's go inside. And to get this direction, we can subtract the position of our voxel. So let's do a subtract, and we will promote the second input to a constant. So let's do a constant. Let's switch this to a 3 floats, and we will leave this at 0, 0, and 0, which is the center of our scene. And we also want to normalize this vector. So let's do a normalize from here. And we can do a bind export and export this as our new vel field. So let's do new vel over here and set the type to be a 3 float. And we don't actually need this density output anymore. So if I were to go up, let's drop down a null and let's rename this to new vel. We can visualize the trails here better if we do a volume slice from here, and we will plug this volume slice inside a volume trail. And let's point our second input to our velocity field. So let's do something like this, and we can kind of see our vectors pointing towards the center of our scene. And we want to make some room over here, and we also want to add some velocity noise to this. So after, or rather before our null, let's do a velocity, or rather a volume velocity. So we will drop this here, and we want to turn on the option for the curl noise. So let's turn this on, and we will reduce the scale here, and let's maybe also reduce the swirl size, and I'll leave the grain as it is. So this by default is also animated, as we can see, and I believe this will be fine for now. So let's make some adjustments to our vector over here inside the volume VOP. I actually want this vector to not have any magnitude on the Y direction. So we want this to be flat, so all of the vectors will point right in the center of our object. So we can do this if we do a multiply here after our subtract. Let's do a multiply and also promote the second input to a constant. And for the constant here, we will switch to 3 floats, and we will do 1, 0, and 1. So now this essentially means that we will have no movement on our up and down direction. Okay, and we will also want to further control this vector, so we can do another promotion here for this input 3. Let's promote this to a parameter, and we will rename this to, let's say, pull strength. Alright, so we give it this name, and we can go up, and now we can control how much we want this to take effect. We will also want to combine this vector with a vector that goes straight up, so we can also help our smoke achieve that verticality. Let's go back inside here, and let's simply do a parameter for this, and I will rename this to up vector. Let's do a 3 float, and let's just simply add this after our normalize with our other vector. So let's do an add here. Let's add these two and export this to our new vel, and if I go up, I can increase the second value here to increase our upwards motion. So let's leave this maybe at 0.5. And now we actually made a mistake. We can see that this pull strength is not having any effect, and this is because we have to do this after we normalize it. So let's get rid of this third input here for our multiply, and let's do another second multiply after the normalize. And let's promote this one instead, and this will be our pull strength. Alright, so now if I go up, I can control how much we want to pull this, but actually we can see that here we are pushing out the smoke rather than pulling, so we have to go back inside here, and let's reverse the order of this subtraction. So I will press Shift R while selecting this node. Okay, so now we can see that the velocity field points up and also towards the center as well. So we can now control this movement over here. So something like this, I believe, will be fine. Let's source this in and see what we get. So we will also merge this. So this new vel I will place inside this merge. And let's go to our Pyro solver inside the sourcing tab. Let's hit plus. And we will do the same pull operation for this. So let's switch this to pull, and we will set this to vector. The source volume, let's point to our new vel that we just created. And the target field will be the regular velocity. So just vel. And let's also turn on direction strength, and we will set the acceleration maybe to 5 as well. And let's see the result that we get now. So overall our motion will be more vertical, and it will also help our smoke not go to the sides as much, so it will maintain this verticality even more. So I believe something like this is actually looking pretty good, and this doesn't need to be a high resolution since we are just using this to advect our points. And we can go ahead, and from here we will do a file cache, and let's set the base folder. Here I have a job variable. Let's rename this to vel field. And since we are going to speed up our simulation later, we will need to cache a lot of frames. So for this animation, I ended up caching 600 frames. So for our end timer here, let's do from 1 to 600. So then we can speed up the simulation and do different time shifts, so we will have enough frames to work with. And I will save to disk. So from here we can append the null, and this will be our vel. And now for our particle simulation, we will use the same base as we did for our pyro. In fact, we are going to grab all of these 4 nodes. Let's Control C and let's bring them over to the side. And let's look at the result of our blast, and we will need a little bit more points for this. So for our scatter, I'll just increase this, and we can go back and adjust the amount that we need. But for now I know that we just need more points. So let's drop this into a pop net, and inside here let's turn off guides and emission type all points. And for our birth, let's use life of 2 and variance of 0.5. Okay, so now we can do a pop advect by volumes, and we have to go to our velocity. So let's go up, let's grab our vel, Control C, and let's bring this in over here at the SOP field. So let's paste this here, and for advection type we will do update position. Let's do velocity update final velocity, and if I play the simulation, this is the result, and we can see that we have this ugly stepping going on over here. So to fix this, let's turn off use the expression, and the expression here will be vel scale multiply equals fit, and in parentheses at age let's do from 0 to 0.2 to a value of 0 and 1. So I go more in depth about this in my fixed particle stepping video, so go ahead and check that out if you want to learn more. But now essentially this should blend in the position. So we are mapping the velocity scale on our age. So now we are blending the velocity scale in over a time period of roughly 0.2 seconds, which is this value over here. And as a result, now we should have a smooth motion. Okay, so this is looking pretty good. And now for the second thing that we want to do here is make our particles thinner as the simulation progresses. And this is a technique explained in my volume sample and volume gradient video. So I also recommend checking that out as well if you haven't already. So let's go ahead, and we will need to create this gradient field, and we will base it on our velocity. So going up from this velocity, let's do a volume analysis. And we want the source group to be density. So we want to compute the gradient of this density. And let's do another null here, and let's rename this to gradient field. And we can go ahead and grab this. So let's Control C. Let's go inside our PubNet, and we will duplicate this pop.vec by volumes. So let's hold Alt and duplicate this and plug it in our chain, and now we can point our SOP to this gradient field that we created. And we have to change the field name here to density, since density will be the field that we base this on. And by default, a velocity scale of 1 will give us super wacky results. As we can see, we just have to lower this velocity scale. So let's do something really low here. Let's try maybe a value of 0.1, and let's play. So now this is slightly better. We also don't want to update the velocity, so we don't want to propagate the velocity to the next frame. So we will set this to no change. So now we are having a slightly better result, but still this is way too strong. So let's do another 0 here, 0.001, and let's press play. Okay, so now this is more the result that we are interested in. Alright, so probably this velocity scale of 0.01, I think this is looking pretty good. So let's go up and let's take a look at our simulation and see how many points we are working with. I know I need roughly around 500,000 maybe to make sure that this is a high quality simulation. Let's maybe just increase the scatter. We currently have 200,000. Let's maybe just double this. So let's increase this to maybe 10,000 points scattered here. Let's simulate, and probably this is good enough. Because we are going to duplicate and time shift this, I think this will do just fine. So we can go ahead and cache these out. So we'll do a file cache, and we also want to cache the entire 600 frames that our volume simulation is. So let's Control Shift click over here and set this to 600, and let's save to disk. So after we cache this out, we can do a retime and we can speed this up to make it more energetic. So let's use a speed value, let's use 2.7, and for output and input frame range, let's set the input frame range to 1 to 600, which is the amount that we cached. And also we want to extend the output frame range outside of the scope of our timeline. So let's use Control Shift click, and let's also output maybe 250 frames. Because later we are going to do multiple time shifts, we are going to push the simulations further in the animation, we want to make sure that we have enough frames to work with. So like I mentioned earlier, let's do a time shift from here, and let's add a few frames to this. So in the expression here, let's do $F, and let's add maybe 25 frames. Just so we start with the shape of our simulation already created. So we end up with something like this. And now what we can do is let's template our tube. So this tube over here that we said we were going to use for the reference, for the size reference, let's template this. And this is probably looking pretty fine. We can, however, do a transform here, and we can play around with the settings. So we can make this taller or shorter. Let's maybe make this a little bit taller, and we can go ahead and right click this first value of the scale and paste relative references here, and we can also maybe scale this down in the X and the Z directions. So we can do something like this, and we will use a super advanced technique here to instantly add more details to the simulation, and this is very advanced. What we can do is we can do another transform here, and we will rotate the scale on the Y value. So let's maybe use a value here of 120, and now we can grab our original simulation and let's do a merge, and we will merge this on top. So as you can see, this is super high level stuff, and this is the real secret of Houdini. Okay, but jokes aside, this is just a very simple way to add more detail to the simulation. And since we have enough frames to play with, we can also do a time shift here, and we can also push this further in the animation. Let's maybe add another 20 frames here, so we can just offset the animation and really create more detail. So we end up with something like this, and I think this looks pretty good, and we can untemplate our tube. Now let's do another taper from here to actually create the shape of our sphere. So let's drop down a linear taper, And again I will press enter, and let's use N to feed capture and B to cycle. Okay, and instead of using the handles here, I will turn on this enable ramp option, and I will use this instead so we can have the complete control. And I will maybe expand this window, and let's go ahead and start to squeeze this together at the top. Let's do something like this, and I might want to increase this at the bottom actually, so we can extend the values over 1 if I use my scroll wheel here. And I will set all of these points. Let's shift click and let's set them to B-spline. So let's try something like this. Let's make a nice interesting shape for our sword, for our spear rather. So we end up with something like this, and I think this looks pretty good. And we can later go back and adjust this shape if we want to. And now before we do the coloring, we actually made a mistake earlier when we created our attribute noise float. This one here, the color is actually supposed to be a vector. So let's switch this to a vector type, and I will drop down an attribute VOP, and let's grab the first component of this color. So let's do vector to float. And we will assign the first value here as our CD. So now if I go up, we can see that we do still work in black and white, but we have this color information that is a 3 floats. So unfortunately we have to go again and resimulate all of this. So let's save to disk. So now to color our particles, let's do an attribute VOP, and we will base this color on our already existing color information. So let's rename this to setCD. Let's go inside. And let's plug the CD back inside our CD, and we will filter this through a ramp. So let's do a ramp parameter in between, and we will also want to multiply the overall strength of this color. So let's do a multiply here. Let's promote the second input, and this one will be strength. And we will go up and let's set this strength to 1, and let's set the display here to pixels, and we will do an orange to black gradients, sort of how we usually color our fire. So this second value here for this handle, let's use an orange. So let's introduce a little bit more red in this. Let's do something like this, and if I increase the strength, we should start to mimic sort of like what flames do. Maybe we want to introduce more red into this, and maybe a little bit more white. But I think something like this should be fine. And I will go to this taper here, and probably I will adjust the overall scale of this, or we could go to the transform, and over here we can decrease the size on the basically the spread of this effect. So I think something like this is looking pretty good. And one final thing that we want to do for our particles is I want the particles that are further away from the center of this sphere, I want them to be more transparent. So let's do another attribute VOP from here. Let's rename this to set alpha, and we will use the alpha channel to preview this in our viewport, but really we are going to control the Pscale of the particles. And to create this gradient effect from the center, we can use a helper geometry. So let's drop down a tube next to this, and let's template this, and I will press enter, and we want to create sort of the same shape of our simulation. So let's bring this up slightly, and let's decide how big we want our base, maybe something like this. And for our scale at the top, we will bring this in almost completely, like so. So we're going to turn this into an SDF, and we're going to control the opacity of these points based on how further away they are from the SDF. So in order to turn this tube into an SDF, we have to make sure that we select this end caps option here, and we will do a VDB from polygons, and we might as well increase the resolution here. So let's do a voxel size of 0.05. We will do fill interior, and for the exterior band, let's use world space units. And I can press W in my viewport, and if I increase this, we can see how further away we are looking from our geometry basically. So I believe I can template this, and I believe this will give us enough information. We probably don't even need as much exterior band, but let's maybe just set this to a value of 0.5, and I believe this should be fine. So inside this set alpha, I will plug this as my second input. Let's go ahead and preview this result, And let's go ahead and step inside, and we are going to use a volume sample to get our SDF information. So from op input 2, let's do a volume sample, and let's plug our position inside the sample position, and we will want to fit this value to our own custom needs. So let's do a fit range from here, and let's do a bind export, and like I mentioned, we will preview this by using our alpha channel here. So let's set this to alpha. This is with capital A. So for this fit range node, the source max will control how further away it is from our geometry. So let's leave this at a value of 1, and we want to switch the destination min and max. So let's reverse this, and the destination max becomes now 0. And essentially now is if I decrease the source max, so the range that we want to look out further from the geometry, if I decrease this, we can start to see that we fade out our particles that go further away from the geometry. So let's maybe try something like this, and we can also decrease the source min here to also look inside of our SDF. So I can also use a value here maybe of -0.2, and we can further control this by using a ramp as well. So we will use a ramp parameter here. Let's set this to spline ramp. Let's go up and let's reset this ramp, and we will do an exponential ramp here. So let's do something like this, and select all of these, set them to B spline, and we can see if I turn this on and off, the result that we get. So I think this is looking actually pretty good, and like I mentioned, we are just using the alpha to preview our result in the viewport. We want to export this to our Pscale, so let's use a bind export here and set this to Pscale. So this is what will actually make our particles fade in the render. So I believe with this we pretty much have everything we need. The only thing we have left to do is to do the other side, and for this we will just drop down a transform and rotate this 180 degrees. And we also want to use a time shift here as well, because we have enough frames to play with. And again, I will maybe push this forward in time, maybe let's say 15 frames. Okay, so now when I do a merge, this will be our final result. And now we can grab our extracted point from over here. Let's grab this, let's do an object merge and bring this over, and let's do a copy to points and see how this looks in our animation. So let's take a look at the result, and let's take a look at our crag animation. So if I go in the camera, this is what we end up with. Now this is slightly offset from where it needs to be, and we can adjust the position for this. Maybe we can actually go to our transform properties over here, and for our reference geometry we can adjust the height of our object. So this second one where we decided our height, I can actually play around with this value to have the correct offset here. Alright, and for the handle in the original render I just added the tube, so I don't think that this is necessary to add it. And we can still go ahead and make further adjustments here. If, for example, I want to bring this down a little bit, we can go over here after we, or maybe we can go all the way to the top, and I can grab this transform, and I can adjust the translate Y value here to bring this closer, like so. But probably this should be done at the end after we do our alpha. So let's use a transform here instead, and let's reduce the translate Y. So we bring this closer to his hands, and this is the result. So we can do a flip book on this. So we end up with something like this. Okay, so this is looking pretty good. And this is the main effect that I wanted to show you. And now I will just break down the other elements that I added to this shot, and maybe show you a little bit of the compositing that I did. So let's go up, and this is the effects that we created just now. And here we also have a ground geometry. Okay, and a fog layer like this. As far as the ground is concerned, if I step inside here, we can see that this is just a simple grid, and let's hide other objects. So this is just a grid with a lot of resolution and a UV texture, so we can map our material. And I also added a mountain node to slightly alter its position a little bit, so we are running a noise over this grid with a very small amplitude. And for the material for this, I believe that I used a Megascan texture, this Icelandic rocky ground texture. Okay, so pretty simple, and also the light is very simple. We just have a sun basically that's pointing behind our character. So this is just a regular sun with all of the default settings. And finally here for our fog, let's step inside, and I'm using the Camera Frustum HDA. that I created, and I will also include this in the downloads if you follow the download link in the description, which is just pointing to a camera and it's creating a geometry based on what the camera sees. So we are freezing this at the beginning of the animation and also at the end, and we are now using a Boolean union operation to get rid of any inner intersections between these two objects. So by combining these two time shifts, we are going to cover the entire area that the camera sees at any given frame. And we don't have to compute this each frame. So from here we turn this into a fog, and inside a volume VOP, this is where we do most of our operations. Let's step inside here, and we are just grabbing the density and multiplying this by a few things here. So for now I will get rid of this connection, and the first thing that we are doing is we are fading this out from the camera. So this is where the camera position is, and I'm bringing this into our second input over here. So I'm doing an object merge for our camera. I'm using into this object for the transform setting here to bring this into the world space of the camera, and also I'm packing before merging, so we only have one point. So when I bring this in our volume VOP as the second input, from here we can do a distance from our voxels to this position of the camera, and I'm using a fit range to decide what part in front of our camera I want to fade out. So if I increase this, we can see that I bring out more or less of the fog that's in front of the camera. So this was a value of 25 here. And then we are also combining the bounding box of this whole volume. So if I plug this back in, we are using a relative to bounding box node that we are pointing to our cells. So the input here is first input, which is the entire volume basically, and we are sampling this from a position which we also alter with a noise. So for example, if I were to disable this and just use the position without this noise, we can see that this is the result. This is giving us a vector result, and we are going to use the height of this vector, so essentially the y value here, and we are filtering it through a ramp. So if I go up, we can control how much we want to fade it from the top by altering this ramp like so. And then we are just adding a turbulent noise, 3D noise to our position where we generate our B-box, so we can also add some noise. And if I go up, I also animated this on the Y offset. So if I play my timeline, we have some subtle animation, but I don't think this really makes much of a difference. So maybe this offset value doesn't need to be animated. Finally, we have a Pyro bake volume, and this is only for visualization. I set the density scale here to a value of 0.1. For the material for this, it's a very simple redshift material. So in the material tab, for our volume, we have just a volume shader here set to channel density and a scatter coefficient of 4 and an absorption coefficient of 3. So this is going to make our smoke slightly more thicker. Also in the material tab for our particles, we are creating a simple material that has the weight of the color set to 0. We don't have any reflection, so this is also set to 0, and we are only using the emission, which has a weight of 12, and the weight here controls how much GI we get from our effects. So if I were to increase this value, we would get more bounce lighting throughout our on our mesh and also throughout our volume as well. So in my case, a value of 12 gave me the result that I was after. And for the emission color, we are just bringing in our CD by using a particle attribute lookup. So very simple stuff, and I went ahead and rendered this, and let's head over to Nuke and see what we get. So this is where we end at, and we start from a similar result to this. So we don't really do a lot of modifications, but this is where we start. So right away we are going to shuffle the diffuse and the specular and the reflection, and if I merged all of these together, this will give me what's essentially the beauty pass without all of the fog, volume and emission. So from here I also bring in the depth channel. So if I press A, I shuffle the depth inside the alpha, and I use it to create this black and white mask to grade essentially the ground that's right in front. So when I preview the result here with this gray node, we can see that I'm darkening basically what's right in front of our camera. So this just adds a little bit of detail and layering to our scene. And over here we have, so this will be our volume that we get from the light, which is our sun. And then over here to the side, we also have the same volume that's essentially coming from the sun, but we also have it combined with the GI. So for example, if I do a merge operation and set it to from, we can subtract only the GI that's affecting our volume. So this is the GI from the emission. I'm running a noise reduction on this. So this is the neat video noise reduction, which works slightly better than the regular denoise that Nuke provides, but the regular denoise is fine as well. And I'm also doing some grading adjustments for our regular GI on our geometry. I also run the same reduce noise plugin, and then doing some grading adjustments. We bring this together and then we just merge it on top of our chain. So this is where we end up with. Over here we have just our volume that's shaded only by the sun, and we do some grading to this as well. And I also multiply it with a ramp that I created over here just to fade it towards the top, and some final grading here, make it a little bit more blue, and we add it on top. And then we bring in our emission channel, and first I'm using this to shuffle it in. I'm blurring this out and I'm grading this down, so I'm making this darker, and I'm bringing it in as a distortion layer. So over here in this shuffle node, this is set to input A, which is our emission channel, and I'm shuffling in the RGBA into a new output layer that I'm creating here called dist. So this is for distortion. And then I can use this layer inside an iDistort node over here. So we can see that the UV channels are set to this dist layer that we created. And I'm just offsetting the UV scale here so we can control how much displacement we want. And this is something I usually like to do whenever I add my particles. I like to place below them a distortion layer to sort of achieve a cooler look, and it also blends everything together more cohesively. So on top of this, we grab our original emission, we do a blur, and then we do a luminance with a pre-mult, so we can select only the very brightest values. And then I'm using a saturation node to basically turn this into white, and this is going to be the very hot core of this effect. And on top of this, we have the normal emission pass, which is graded down and slightly colored, or I believe we didn't alter the color at all. We just graded this down, so we can see here that I set the gain here to 0.1. And then this layer we add on top, and from the same layer we desaturate this a bit, we do a crop, and we use the AP Glow node, which is a free node from Nukepedia, and it's my favorite exponential glow. So when we add this on top, we end up with our final result. From here we do a crop, I add some motion blur, and I add some final grading adjustments just to increase the contrast. And finally, this real SRegan node here is an upscale node that's based on some AI model, and this is provided on Nuke's Skaterweb website, so I will provide the link for this as well, and we can check out the result. This will by default upscale our result by 4 times, and for some reason Nuke crash, so be careful when you are using this node. But the final result is looking something like this. So we can see that the upscaling node really did a nice job sharpening up everything, and it also denoised our render quite a bit, so I'm really happy with how real SRegan performs. So that's about everything I wanted to cover, and I hope this gave you an idea of some of the things that you can do with the extract transform node, and hope that you can use it in your day-to-day work.